This video is on damping and resonance. Question 1. What is a restoring force? A restoring force is a force which pushes or pulls an object to its equilibrium position. So remember the video on simple harmonic motion, where we learned about Hooke's law. The minus sign is the restoring force. Question 2. What are some characteristics for simple harmonic motion? Period and frequency are both independent of amplitude. Displacement versus time, velocity versus time, and acceleration versus time graphs are sine or cosine functions. Period, and therefore frequency and amplitude are constant, meaning no damping. A stiff spring will have a large spring constant K and therefore a smaller period. Vibrating or oscillating objects with more mass have a longer period. Question 3. Define free oscillation. That's an object oscillating without energy loss. So the amplitude is the same. Question 4. Label and draw a displacement versus time graph for a free oscillation. So it's going to look like this. Question 5. Define damping. Damping is friction which slows down back and forth motion. Question 6. Define underdamping or light damping. Underdamping is back and forth motion which has its amplitude decreased because of damping. So, imagine dropping a tennis ball in water. It's going to float because its density is less than that of water. But the tennis ball oscillates up and down, and its amplitude eventually decreases, and the object eventually comes to rest. That's an example of underdamping. Question 7. Label and draw a graph for an underdamped system. So that's what an underdamped system looks like. Amplitude versus time, the red graph. Question 8. Define overdamped motion. During overdamped motion, an object never reaches the equilibrium position during back and forth motion because of high damping. So imagine releasing a pendulum in mud. The pendulum does not make it to the equilibrium position. The pendulum does not even complete 1/4 of an oscillation. So it's like gonna stop before it even reaches the bottom. Question 9. Label and draw a graph for an overdamped motion. So overdamped looks like this. As time goes to infinity, the amplitude or the displacement does not even reach 0, the equilibrium position. Question 10. Define critically damped motion. During critically damped motion, an object returns to its equilibrium position as fast as possible and stays there because of damping. So example, shock absorbers in a car are critically damped. Question 11. Label and draw a graph for a critically damped system. So that's what critically damped looks like, the one in lime green. Very quickly, the object reaches its equilibrium position. Question 12. What is a driving force? A driving force puts energy into a system at a certain frequency. This frequency does not have to be the natural frequency of the system. Question 13. Define natural frequency. The natural frequency is a frequency at which a system would oscillate if there is no driving force and if there is no damping force. Question 14. Define resonance. When does resonance occur? Resonance is the phenomenon of driving a system with a frequency equal to its natural frequency. This leads to an increase in both amplitude and energy. So a small amplitude driving force can produce a large amplitude response if there is little to no damping. By damping, I mean friction. Question 15. What happens to the amplitude of an object when the natural frequency of the object is much lower or much higher than the driving frequency? So An object oscillates with very low amplitude. So here's an example. Imagine continuously pushing someone on a swing at the incorrect moment when the swing and the push, called the driving force, are both in the opposite direction, out of phase. So here are swings. Question 16. What happens to the amplitude of an object when the natural frequency of the object is approximately equal to the driving frequency? An object oscillates with an increase in amplitude. The amplitude of the oscillation increases as long as the driving force on the object has the same frequency as the natural frequency. So here's an example. Microwave ovens heat food by resonating water molecules. In order to heat the food most effectively, the frequency of the microwave should have a value equal to the natural frequency of the vibration of the water molecules. Here's another example. Imagine continuously pushing someone on a swing at the correct moment when the swing and the push, called the driving force, are both in the same direction, in phase. Question 17. Draw an amplitude versus frequency graph of an object oscillating with a driving force and a damping force. So here we could see if we're pushing with the natural frequency and there's no damping, we're going to get like infinite amplitude. The object is going to oscillate more and more and more. If there's light damping, then you could see the amplitude shifts a bit to the left of the natural frequency. If there's more damping, you could see the maximum shifts a little bit more to the natural frequency. And finally, if there's heavy damping, we could see there's too much friction. It doesn't matter how much we push. We're not going to get large amplitude. And maybe that's what we want for safety. So you could see if the driving frequency is too high, the amplitude decreases. We need to push at just the right natural frequency to get maximum amplitude. Question 18. Two oscillators are experiencing forced oscillations at a frequency near to the natural frequency of each oscillator. The graph below shows the amplitude with forcing frequency for each oscillator. So there's two oscillators, and here are the graphs for both. Part A, which system, 1 or 2, has a greater amount of damping? It's 2 because it's lower. Part B, which system, 1 or 2, has a greater natural frequency of the oscillation? It's 2 because the peak is to the right. Question 19. List some effects of resonance in the real world. Well, we got a bridge swaying. We could see videos about the Tacoma Narrows Bridge, children on swings, a car moving on a bumpy road, or a vibrating engine. And finally, a kitchen microwave to warm food by oscillating water.